Okay. Just give it one more minute and then we'll start. All right, maybe we'll begin. We'll start joining. So welcome everyone to this colloquium, Thursday colloquium. We have this Thursday colloquium now once every 2 weeks. And we moved from in-person colloquium at the Institute to online colloquium about 2 years ago at the time of the pandemic. And then we are continuing the online colloquium now, which allows us the opportunity to request speakers like today's to engage with us at a distance. And so welcome everybody. Today's speaker is Konstantinos Tassis, Kostas for short. He is associate professor at University of Crete and Foundation for Research and Technology in Hellas in Heraklion. He did his early education in Thessaloniki and then got his PhD from University of Illinois, and afterwards had postdoctoral positions at University of Chicago, Caltech, and visiting scientist position at Max Planck Institute for Radio Astronomy before joining University of Crete about 10 years ago. So he has a wide range of interests, including star formation in the galaxy and the universe, interstellar medium physics, chemistry, MHD simulations in astrophysical context, and polarization. And it is in this last item, polarization, that over time collaboration has developed between University of Crete and IUCAA through RAM, Ram's lab, where this instrument called WALOP is being made. And that instrument is going to be used for this major survey called the PASIPHAE survey, which Kostas is going to talk about today. So this is important for characterizing polarization foreground for cosmic microwave background polarization measurements, for example. So without further ado, I would request Kostas to begin his talk. Welcome, Kostas, and all yours.
Thank you. Thank you very much for the kind invitation to talk about the experiment that Ram, Tony Ritchett, and I are leading. The experiment is called PASIPHAE, and its aim is to revolutionize the way the foregrounds due to galactic interstellar dust is removed by experiments seeking an inflationary signature in the polarization of the CMB. PASIPHAE is an acronym. It stands for Polar Area Stellar Imaging Polarization High Accuracy Experiment. It's a bit contrived, as you can see. And the reason is because it is also a name, like Gaia. It is the name of the Minoan queen. As here in Greece, IUCAA, of course, the South African Astronomical Observatories, Caltech in the US, and the University of Oslo in Norway. And at the bottom, you can see our sponsors so far. And this is the family portrait since our last collaboration meeting in Norway right before the pandemic. So, PASIPHAE aims to address the thermal dust polarization foreground of the CMB. As we all know, the polarization of the CMB probes inflation. But the early universe is not the only source of polarized microwave emission. Cold, elongated galactic dust grains also align with the galactic magnetic field and so emit polarized microwaves as well. The polarization direction depends, in this case, on the direction of the magnetic field. So the way the dust foreground is subtracted from the microwave maps is the following. Here I'm showing various contributions to the microwave sky. It's a busy plot, so let's focus on the two ingredients that are relevant to the problem, the CMB and the dust, the thermal dust. Galactic dust, although it's very cold, around 19 degrees Kelvin, is still much warmer than the CMB, which sits at 3 Kelvin. So it dominates the emission at higher frequencies. So what we do is we map the dust emission at higher frequencies where it dominates, say in the 353 gigahertz Planck channel, and you scale and subtract the signal from what you see at roughly 100 gigahertz, where you expect the cosmic signal to contribute significantly. This technique works very well for scalar quantities such as intensity. And so the CMB science so far has been extremely successful despite the presence of galactic dust. But not so much for polarization. And there is a problem which is much more severe than originally thought. And it has to do with the three-dimensional structure of the ISM. As our group first pointed out in 2015, you can get a situation like the following. You may have two clouds that lie along the line of sight. One dominates the emission at high frequencies because of temperature differences, and the other at lower frequencies. The polarization pattern then rotates between these frequencies, trying to trace the magnetic field of the dominant cloud in each case, if the magnetic fields are not aligned. This line of sight frequency decorrelation of the polarization pattern has been studied by several groups since, but there has not been a consensus among these studies because the effect remained elusive and unconstrained until very recently. Now, there is evidence that this effect is actually present and significant in Planck data, as we showed in 2021, last year. The key in the identification of the effect is to know where to look for it. And that's where 21 centimeter data come to the rescue in two ways. This is atomic hydrogen emission from neutral gas in our galaxy. And first of all, it helps because, as you can see in this cartoon, atomic H1 spectra can be used to identify locations on the sky where the line of sight intersects multiple clouds. And second, they can also help to approximately estimate the magnetic field direction in each cloud. Indeed, high-resolution atomic hydrogen spectra reveal thin linear structures, filamentary structures that are statistically aligned with the magnetic field. So the direction of the magnetic field could be inferred indirectly from the morphology of the H1 clouds. It's not a perfect way to do these things, but it works in a statistical sense. So using this H1 data, we identified sightlines that were susceptible to this line of sight frequency decorrelation effect by intersecting more than one clouds with misaligned magnetic fields. These locations make up our target sample, where the sightlines intersect more than one cloud. While if the sightline intersects only one cloud and there is no line of sight frequency correlation expected, then these pixels make up the control group. Right? And here are the locations of target and control pixels on the sky. The red pixels belong to the control, and these whitish pixels to the target. So we go to the Planck polarization data, and for each pixel in the target and in the control sample, we compute how much the polarization direction changes between Planck 353 gigahertz channel and 217 gigahertz. Because the target sample pixels are selected to have a higher likelihood of larger line of sight frequency decorrelation, we predict larger angle differences between the two frequencies than for the control. And indeed, this is exactly what we see. Here I'm showing the distribution of polarization angle changes between the two frequencies, 353 gigahertz and 217 gigahertz. And I show it for three separate sets of pixels. All the Planck pixels of the high galactic latitude sky is black, is shown in black. The control pixels are shown in blue, and the target pixels in orange. This D is the spread of these distributions. The difference in D, in the spread between the target and the control samples, that you can see even by eye, is statistically significant and is robust against how you subtract the CMB, what algorithm you use to make the maps, the noise level of the two sets of pixels, and the residual systematics of Planck. In fact, correcting for Planck's residual systematics increases the significance of the effect. And let me remind you that this selection of target and control pixels, right, is completely astrophysical and knows nothing about Planck and its systematics. And not only is the spread D between the two frequencies, the target and control samples, different, but it also increases as the misalignment between the clouds, shown here on the x-axis, increases, just as we predicted back in 2015. This is mostly the work of Dr. Vincent Pellegrims, who is a postdoc here in Crete with us. And now that we have demonstrated that this effect is visible in the Planck data, the need to find ways to account for it when cleaning the microwave maps before using them to study the early universe got more urgent, right? And PASIPHAE seeks to remedy that exact effect. So, the same dust grains that emit polarized microwaves and cause all the trouble also absorb starlight and impart polarization on the emerging light. So we can use stars of known distances as lampposts. If we measure the polarization of many stars of different but known distances along the line of sight, then we can infer the direction of the magnetic field between them and use this information to subtract the dust foreground from the CMB polarization, including the three-dimensional effects. This approach is only now possible because of Gaia and PASIPHAE. ESA's Gaia mission has delivered reliable parallaxes for billion stars, right? A billion stars. And PASIPHAE will deliver the necessary polarization measurements. And for the first time, we'll be able to construct a tomographic map of the galactic magnetic field directions. Okay. The PASIPHAE survey will cover the high galactic latitudes that the CMB polarization experiments target, and it will run concurrently from two sites, in the northern hemisphere at the Skinakas Observatory here in Crete, and in the southern hemisphere at the South African Astronomical Observatory in Sutherland. These are the vitals of the survey. Basically, we hope to cover 5,000 square degrees per year. PASIPHAE will measure the polarization of several millions of stars in a part of the sky that is essentially unexplored in optical polarization. I'm showing here the number of stars per square degree with currently measured polarization properties as a function of galactic latitude. The high galactic latitudes of interest have been completely neglected, and the current state of the art is disheartening at less than 1 star per 3 square degrees. The reason, of course, is because the whole thing is driven by the star formation community that cares about the galactic plane where stars are forming inside molecular clouds. PASIPHAE, though, will take us to at least 300 stars per square degree. This is a 1,000-fold improvement over the current state of the art. Now, to achieve this, both systematic and statistical uncertainties need to be at or below 0.1%. We need this kind of accuracy, which is unprecedented for wide field surveys because of the fact that at these high galactic latitudes, there is little dust, so the polarization is low. This is achieved by WALOPs, two innovative wide area linear optopolarimeters designed by Professor Amapraka's lab at your institute specifically for this project. The WALOP builds on the well-tested, no moving parts, low systematics, 4-channel technology of a smaller instrument, smaller polarimeter, also developed by RAM, which is called RoboPol, that has been running at Skinakas with tremendous success since 2013, but it implements this technology at a very wide field instrument, which WALOP is. The field of view is half a degree on the side. The WALOPs are, as you know, developed currently at IUCAA, and we expect commissioning of the southern instrument this year. I am not the right person to talk about these instruments, right? Any questions you might have, Ram, who is the expert, can answer. And I'm showing here also 2 PhD students involved in the design that you know, Sid and Johnny. All I'm going to say, though, is that these instruments, by performing differential photometry in pairs between the images, the 4 channels, projected on 4 different CCDs, that's why they have 4 arms, measure the Q's and U's, Stokes parameters, with a single exposure. And let me remind you that the Stokes parameters describe the polarization of a beam in terms of observable intensities with polarizations along different axes. To describe linear polarization, which is what we are interested in, we only need the relative Stokes Q and relative Stokes U, that is to say the ratio Q over total intensity I and U over total intensity I. Q is the difference of the intensities with polarization along the X and Y axis, while U is the difference of intensities with polarization along these alpha and beta axes, which are rotated with respect to the XY axis by 45 degrees. So if I construct on a QU plane now, as shown in the upper right corner, a fully polarized beam with horizontal polarization, this will sit on the Q-axis at Q equals +1, as you can see marked by the star. A fully polarized beam, on the other hand, with vertical polarization, will also sit again on the Q-axis, but it will now have a -1 value. And a fully polarized beam with a polarization at 135 degrees will sit on the U-axis at a value of -1. So generally, more generally, the distance of a measurement on the QU plane from the origin give us the degree of polarization, P, that you can see here, while the polar angle from the +Q axis is twice the polarization angle, which is here denoted as chi, the Greek letter chi, or and in the literature is also called EVPA, electron vector position angle. Since we are pushing the envelope of polarimetry with this program, systematic uncertainty is a major obstacle for reaching these low optical polarization levels expected at high galactic latitudes. The reason is that the calibration of the polarimeters on the sky is done with the use of standard stars, and those are not known with adequately high precision currently. The last 5 years, we have been monitoring 121 candidate standard stars all over the area, all over the sky with RoboPol. And we have discovered that many of the standard stars currently used to calibrate polarimeters are in fact variable and unreliable. we can see here at the top a sample of measurements of unpolarized standards on the QU plane for different years of observations. Currently, 80 stars in the sample are judged as non-variable, reliable standards, and you can see their location in the sky on the lower panel. The full list of polarimetric standards, stable down to 0.1%, will be published soon. This is work led by Dr. Dmitry Blinov, who has also spearheaded most of the work of RoboBall in general. Okay, so let's say that we managed to observe polarizations. So let's take a brief look now at how we plan to perform tomography on the polarimetric properties of interstellar clouds once the WALOPs are commissioned and PASIPHAE starts. In this cartoon, I saw the situation we are faced with, right? Multiple clouds along the line of sight and stars interspersed between them. Each star is affected polarimetrically only by clouds in front of them. And at the low polarizations that we are working on, the low polarization regime at high galactic latitudes, Q's and U's due to each cloud, right, the contribution of it due to each cloud are additive. So the Q's and U's are additive. And we want from observations of Q's and U's for each star and the knowledge of the distance of each star combined, right, for all the stars along in the beam, along the line of sight, to figure out as much as we can about the clouds and their magnetic field. So let's see how. We employ a Bayesian approach. We construct a likelihood function for each sightline, and each cloud adds 6 parameters to the likelihood. The distance of the cloud, the mean Q value that this cloud alone would be introducing to a bunch of stars behind it, the mean U value of the cloud, so Q and U, the distance 3, and plus 3 parameters describing the intrinsic scatter of Q's and U's that each cloud contributes or induces because of turbulence. We float the number of clouds in each sightline and explore models with anywhere between 1 and 5 clouds, because this is what we expect from H1 spectroscopic surveys. We select then the number of clouds that best describe the data based on the computed evidence. We compute the Bayesian evidence for this. We validate our algorithm using a large array of realistic simulations. Here is such an example of a simulated field with 2 simulated clouds along the line of sight producing the observed polarization. The field is half a degree on the side, and we consider this to be a single sightline. The segments you see here represent simulated polarization observations for each star. And this is what these observations look like on the QU plane. And here is what happens once I encode the stars by distance. The color bar now shows the distance modulus, which describes the distance in logarithmic fashion. Darker bluer points correspond to nearby stars. Here I plot separately the Q's and U's as a function of distance modulus for all the stars, and I have suppressed the error bars for clarity. The first cloud, you can even see by eye where it's located. It's where the polarization jumps above 0. This is the same data, but combined in a single plot, still showing Q's and U's with different colors, right? And this is the result of the tomography analysis algorithm. On the left plot, you see the algorithm maximum likelihood values for the location of the first and the second cloud, the mean Q and mean U with green and purple respectively for both clouds, and also the 1 and 2 sigma uncertainties for each of these quantities. In the two middle plots, I saw the posterior distribution for the cloud distances, and with the blue vertical line, I saw the true location of the clouds. And in the rightmost two plots, I show posterior contours for the mean Q and U for each cloud, while the blue cross shows the true values of these quantities. As you can see, the algorithm is spot on. And the amazing thing, in my opinion, is that we can actually recover not just the Qs and Us for each cloud, but also the distances of the location of the clouds with very high accuracy based only on polarimetric data. There are no other priors, such as extinction, right? Dust information, nothing here. Only polarization. And while the WALOPs are being developed in Ram's lab, we have used Roboball for a pathfinding first demonstration of this magnetic tomography technique. We have taken data for over 1,500 stars in this roughly 2 square degree patch on the sky with Roboball. And the idea is to test our algorithms, use it as a sandbox, right, to test our algorithms in real data. The color bar in the background shows the H1 intensity, and the colors of the segments indicate the distances of the stars. So we have selected this subregion that I'm showing here with a square for our experiment, where the sampling density is higher. And we have applied the Bayesian algorithm I described before for different sightlines, scanning the region as you can see here. So note that each sightline now, as we defined it, is not independent from the others, right? They include the included stars overlap. Right? So let me show you some preliminary results of what we get. Here on the left, I show again the data, and on the right, I show the results. This is a cone, right? So we take a projection on the horizontal plane in the middle, and on the vertical on the right. In the upper panels, in the upper plots, I show the polarization fraction, and on the lower plots, the polarization angle. Redder for positive angles, greener for negative angles. And clearly, you can see that there is significant structure and misalignment, right, of the magnetic field along the line of sight in this cone. And we can recover it with this algorithm. This development and testing of the tomography algorithm is mostly the work of Vincent Pelgrims again and Gina Panopoulou. Gina is a Hubble Fellow at Caltech. She was a PhD student with me, and she has worked closely with us for Roboball. Ram has mentored her as well, and now her career is taking off. Okay, so say we got the 3D map of the galactic magnetic field directions, right? How can we use this information to aid the CMB foreground subtraction? The obvious question is that PASIPHAE maps polarization and absorption, but CMB foreground is in emission. How do we connect absorption and emission, right? Is the polarization due to absorption predictive of the emission polarization? The answer is yes, right? We take advantage of the fact that optical stellar Qs and Us in absorption are extremely well correlated and predictive of the emission Qs and Us, as Planck has shown. What happens right now in the so-called map and subtract scheme that I described before is that a modified black body model for dust emission is fitted per pixel on the sky based on high frequency data, 353 gigahertz, and extrapolated to lower frequency data where the CMB is expected to be around 100 gigahertz. What we are proposing is that we can instead fit a fancier model with a modified black body model fitted per cloud. using H1 intensities to scale their emissivities, and magnetic field direction in each cloud measured by PASIPHAE to set the relative values of Q's and U's that give the polarization angle on the plane of the sky for each cloud. If you have more than one cloud along the line of sight, then you naturally add up the Stokes parameters as we saw before. Then one can use this model that includes the three-dimensional effects to subtract the foreground. Our colleagues at the University of Oslo are developing this method, Professor Inge Anvehus and Hans Christian Eriksen, and Dr. Gerlow and students Trygve Svalheim and Artem Basirov. All of these, though, work so far make use of the property of dust polarization to trace the orientation of the magnetic field, right? Now, going beyond the orientation, we can estimate the strength of the field in each cloud as well. The first method to estimate the magnetic field strength in the interstellar medium using polarimetric measurements of dust was developed by Davis and Chandrasekhar and Fermi in the 50s. Think of a cloud in the interstellar medium permeated by a magnetic field, shown here with the red segments. If the magnetic field within the cloud is uniform, then the polarization map will look uniform as well, right? Like the one on the left. If something perturbs the magnetic field, the polarization map will become dispersed as well. The larger the perturbation compared to the mean field strength, the larger the dispersion in the polarization angle map. So if you measure the dispersion of the polarization map, the dispersion of the angles, and you know something about the cause of the perturbation, you can learn something about the strength of the field. This is the basic idea of Davis Chandrasekhar Fermi, DCF for short. The DCF method assumes that what perturbs the magnetic field is Alfvén waves. Alfvén waves are incompressible transverse oscillations of the magnetic field lines, similar to the oscillations of a guitar string. In the first animation on the left, you see a standing Alfvén wave, and in the second animation on the right, you see the traveling Alfvén wave propagating parallel to the mean field orientation. The blue lines correspond to the magnetic field lines, right? And the black dots to the gas particles. Gas particles are perfectly attached to the field lines and both oscillate in phase, which is what DCF also assumes that is the case in the interstellar medium. And that's a pretty good assumption in most cases. Because of this perfect attachment, the kinetic energy of the gas is transformed to magnetic energy and vice versa, leading to equipartition between the two types of energy. This is also a central assumption of the DCF method. So let's write down these assumptions as equations now. We have the magnetic energy density, which contains three terms, right? The energy density of the mean field, the energy density of the fluctuating field, and this cross term. Alfvén waves are transverse, which means that fluctuations are always perpendicular to the mean field, so the cross term vanishes. The energy balance implies equality then between kinetic energy and magnetic field energy in the fluctuating component, right? The fluctuating field. By dividing both sides with the mean field square and by taking a square root, we can derive this equation for the magnetic field, the mean magnetic field. There are three quantities to estimate here. The density of the cloud, which we can get from emission lines, the turbulent velocity of the cloud, which we can get from Doppler broadening of spectral lines, and the fluctuating to ordered B field ratio, which we can get from the dispersion of the polarization angles, right, delta theta. Up to now, the main assumption was that all perturbations were due to Alfvén waves. That is to say, incompressible, right? However, observations paint a different picture. Compressible MHD waves also exist, like the slow and the fast magnetosonic modes. So even if we accept that all perturbations start out as Alfvén waves, there is a wealth of instabilities that provide mode coupling, and as a result, compressible modes are unavoidable. Indeed, observations show that diffuse interstellar clouds are supersonic and highly compressible, which means that there is significant power in the compressible modes. And these are completely neglected by the DCF method. The compressible modes will contribute to both the gas velocities and the fluctuating to mean field ratio, so omitting them may not be such a good approximation after all. So, with my current PhD student, Rafael Skalidis, whom you can see here, we thought we could try to bring magnetic field strength estimation into the precision era as well. And here's what we did. On the left here, you can see the derivation of the DCF equation again. In brief, we have a mean field, which we perturb. Since we consider only Alfvén waves, the cross term, right, or in the magnetic field energy density is 0. However, in the compressible regime, the cross term is not 0. It can be analytically shown, actually, that the cross term is connected with the density fluctuations. So, going back to the magnetic energy density, the 0th order term corresponds to the mean field energy density, which exists even if we do not include this one, right? Even if we do not include any perturbations. The cross term induced by these compressible modes and where every mode contributes, right? Sorry, the compressible modes is the first order term, and every mode contributes the second order term, right? Note here that we are exploring a regime where delta B is much smaller than the mean field component. In other words, consistently with observations, we assume there exists a well-defined ordered mean field, and the turbulence is subalfvénic or transalfvénic. So the fluctuations are not dominating the mean field. Under these conditions, we can neglect the second order term and keep only the first one, the first order one. If we now proceed as in the DCF case, we can derive an estimate of the magnetic field strength, with the only difference being that now we keep the first order term, right, in the magnetic energy equation. The result is in the equation with a different scaling that you can see here. The fluctuating to order magnetic field ratio in the Alfvénic case scales linearly with the Alfvén speed. But now, in the compressible regime, it scales with the square root of it. And this equation here on the right does take into account the compressible modes. As in the DF case, delta V can be estimated from the turbulent broadening of the emission lines and the fluctuating to order magnetic field ratio from the spread of the polarization angles, angle distribution, this delta theta. Right? And we tested actually the difference in this spread of angles, delta theta, scaling in terms of the Alfvénic Mach number in synthetic data that we produced from MHD simulations. Here you can see the dispersion of the polarization angle versus the Alfvén Mach number of the simulation ranging from 0.1 to about 2. The black dots show the synthetic data, and the magenta line, the DCF scaling relation, while the blue line shows the scaling of the method we are proposing. As you can see, DCF line fails to fit the data, right? While the scaling of our method fits the data very well. So overall, with this new powerful tool, we plan to use the high accuracy method to, in combination with the PASIPHAE polarization measurements and the Gaia distances, to create a 3D map of the interstellar magnetic field strength and direction, right? Both direction and strength for each cloud individually. And we can do this because we fit, remember, in our Bayesian approach, for the intrinsic scatter, the intrinsic spread of angles, polarization angles for each cloud individually. So we have an estimate of delta theta for each cloud, and that means we can estimate the value of the field and not just the mean direction for each cloud individually. So the idea is to produce a 3D map, right, of the magnetic field strength and direction in the high galactic latitudes. Now, although PASIPHAE science is driven by the hand-3D modes, as we said, that's the main science driver, its impact will be wider, right? First, the 3D tomographic map of the galactic magnetic field direction by itself will revolutionize our ability to approach questions such as what is the origin of the galactic magnetic field? Is the magnetic field dynamically important in interstellar clouds? And even what is the origin of ultra-high energy cosmic rays, which are bent only a little bit. They are extragalactic and they are bent only a little bit by the galactic magnetic field. Secondly, the polarization measurements from our survey will also reveal in stellar astrophysics intrinsically polarized stars, and in high energy astrophysics, synchrotron emitters. And of course, there is a great potential for serendipitous discoveries every time you open a new novel science product. Right? So for more information, I invite you to take a look at our white paper posted on the archive. And our polarimeters and the experiment was also recently highlighted by Nature Astronomy in the mission control section. This happened last year, as you can see here. And of course, you can stay tuned with all the latest updates and developments on our website, pasiphae.science. Thank you very much.
So that was great talk, Kostas. Thank you for this very nice talk.
Thank you. I'm sorry I couldn't be there in person, but
I hope soon you should be here now that traveling is possible again. So I would request people to raise their Zoom hand for questions. We have one hand up, and that is Sanjit. Sanjit, please go ahead.
We cannot hear you. There you go.
I can unmute now. Yeah, very nice talk. I just wanted to. I have two questions. If unless others will come up. So first one is that, see, you already have the Planck polarization map for dust. So I mean, it's a full survey. It's available. And if you combine with Gaia data, then with these component separation methods, you could already have some crude estimate of the decorrelation of the polarization, right? Meaning, PASIPHAE data can make it even better, but can't you use the Planck survey already, because it is the stars are already there in the field? This is the first question.
But the problem is that Planck sees integrated emission through the whole line of sight, right? So using let's say H1 data, you could tell how many roughly how many clouds you have along the line of sight, because they appear separate in velocity space, right?
Yeah.
But you don't really know if indeed they represent different clouds, right, or different velocity components within clouds, right? And you also don't know their distance. So it's not easy to do component separation in a 3D fashion with the information you have right now, because the Gaia distances refer only to stars,
Yeah.
And we don't have polarization yet, polarization measurements for stars. That's what we want to do, right? Planck only gives us the integrated polarization along the line of sight.
That's right. So if you could combine it with H1 data, then it would work, right? I mean that.
Then that's what we try to do. In the beginning, I showed, right, our attempt to approach statistically the effect, right, to quantify this line of sight decorrelation that we predicted, right, and started the whole business. But you can only do this in a statistical fashion with existing H1 data, right?
Okay.
You cannot produce, let's say, a template for foreground subtraction and say, look, at this part of the sky, this should be the effect of the decorrelation, because there are, there is this cloud that go with a magnetic field that goes in this direction, and behind it there is another cloud with a magnetic field going in another direction. You don't have this information, right?
Okay. You need large scale information. Yeah.
You need stars to do this, right? Because only stars have known distances, so they act as lampposts, and you have access to the third dimension. So the third dimension, the line of sight dimension, opened up with Gaia, but only for stars.
Yeah, no, I was wondering, like, if you combine like the H1 data, I mean, basically the polarization data can come later. So, okay, I'll ask you the second question. Maybe that is, the thing is that you have this robable data for 2 degrees patch. So that 2-degree patch data, can you combine with Planck data and then get some kind of foreground subtraction? Meaning, because 2-degree will already give you like close to the CMB peak.
Yeah, so 2 degrees is very small, right? To do meaningful science with it, but I mean CMB science, right? But we obtain this data in these small pods in order to test our algorithms. We have not, it's not finalized yet. This is what I presented to you is just preliminary data for the 3D reconstruction, right? We hope to have the final results in a few months. And once we do have this, then yes, we can go and compare with the Planck data. And this will serve also as a sandbox, right, to test the component separation methods and so on.
Meaning, if you choose, for example, the bicep patch, then that 2-degree in the bicep field is like because L of 70 you can reach, meaning it will see 2-degree would correspond to like probably L of 50, right? I mean, so
the
but
way
the systematics,
yeah. So the parts that I showed you, right, is in the north because we did it with RoboBoy here. The bicep field is in the south. The bicep field is 1,000 square degrees across, right? And I think the useful one, because you also always work in Fourier space, is 1/3 of that, I think, like 300 something square degrees. But you're right. The idea is to prioritize with PASIPHAE areas of the sky targeted by current CMB experiments, and BICEP is one of them, right? But there are others as well, and the Simons Observatory is coming up as well. So yes, indeed, the southern survey will be immediately relevant to experiments. And this is why we have prioritized also the southern instrument, and it will be commissioned first, right, this year.
Okay. Okay, thanks. We'll look forward to it.
Thank you, Sanjit. And is there any other question? Please raise your hand. Yeah, Ram, go ahead.
Yeah, Kostas, can you hear me?
Yeah.
So this estimate of the magnetic field strength in the presence of compressible waves, the new formulation. Is there a way to test that already with data?
Yes. So let me. There have been. So this is a very recent result, right? Let me try to. Can you hear me? Yes. Okay. Let me try to show you some tests that we did on simulated data first. So here we go. Can you see my screen?
Not yet.
Sorry. There you go. Can you see this?
We don't see the screen yet.
Okay, let me try again. Share screen.
Yes.
Okay, now you can see. What can you see?
We're seeing your desktop background.
Oh, okay. Let me then. Okay, can you see the slide now?
Yes. Now we can
All
see
right.
the slide.
So this, in a follow-up paper last year that came out last year, we have tested the DCF method versus our new method in synthetic data from a wealth of simulations. We computed the relative difference of the estimated magnetic field from each method, right, with the actual magnetic field strength from the simulations, because this is known. The relative error is shown here with this epsilon in this figure. In the left panel, the horizontal axis shows the relative error using our method, and the vertical axis, the relative error using the DCF method. Between you can see that the DCF method, the error can be up to a factor of 1,000, right? Thousands. While the error in our method remains below 50% over the entire range of simulations that include very different Mach numbers. So we employed a pseudo simulations with very, very different Mach numbers. On the right, it's a zoom in of this region marked with these dots on the left, and the green shaded region that you see, excuse me, shows the area where DCF performs better than our method. There are a few simulations that are in this green shaded region, but even in this case, our method is accurate to less than 50%, right? So we have thoroughly tested it in simulations, and we are very confident of the result. But also, there have been a number of observational papers that came out the last year, where they employ our method versus the DCF, and in one example, and they find more reasonable results. In one example, for instance, there is a paper where they analyze, they study massive star-forming regions with ALMA, and they try to map the magnetic field in the larger scales of the clouds, and when they perform the estimate of the magnetic field with the DCF method, they find that the region of this region of the cloud is magnetically supported so it's magnetically subcritical, as we say in star formation. That means the magnetic field is stronger than the gravitational energy. And that means that the star formation has a very difficult time to operate, right? Doesn't go, because it has to overcome the magnetic resistance, right? The resistance to collapse because of the presence of the magnetic field, which brings in magnetic pressure and tension and so on, and resists collapse, right? And so it doesn't make sense, because they do see massive star formation going on, very vigorous star formation, right? When they apply our method, on the other hand, they get a slightly supercritical result. That means gravity, indeed, with our method, they find that gravity indeed is slightly stronger than the magnetic field, allowing the star formation process and collapse to proceed. This is just one characteristic example off the top of my head.
Ram,
Does this cover you, Ram?
does that answer your question, Ram? Oh, he has got muted again.
Yeah, I could not unmute myself.
I didn't realize that you had gone mute again.
Yeah.
So,
yes, Tassis, thank you.
okay. Anybody else? If not, then thank you again, Kostas, for this wonderful talk, and wish you all the best for a fantastic PASIPHAE survey. And
thank you.
Look forward to the results. Let me clap on behalf of everyone.
When the WALOPs are deployed, we'll have a big celebration, and hopefully we'll get to meet you all in person.
Yes, look forward to that.
Thank you again.
Okay, bye-bye for now. Thank you. Thank you, everybody, for attending.